Testing, testing, 1, 2, 3, testing, testing. Hello, everybody. Good morning, good morning, good morning, good morning. How is everybody doing today? Hopefully you're all doing all right. Hopefully you're all looking forward to the break next week. Am I a little quiet? Interesting. If you guys think I'm a little quiet, just ask me to, oh, yes, Happy New Year! Should old acquaintance be forgot, etc., etc. Yes, Happy New Year. Yeah. Yeah, if I'm a little quiet here, just ask me to turn up the volume a little bit, and I will. So, I thought I might start off the class today by looking at some statistics for the first midterm, because that might be of interest to you guys. So, it turns out that the average on the midterm, once you correct for the people who received 0, which means they didn't submit, so the average of the people who actually wrote the midterm is an 82. I'm kind of disappointed that, you know, through one thing or another, Avenue never shows a 0 corrected average. So 82 is pretty good. That means that the average on the test was an A-, which means that pretty much the majority of the class knows what they're doing on it. So that's good, because, you know, the test was, you know, things are only going to get more difficult from here, so it's good to have the foundations well in hand. Also, I feel like it was a fair test, given how far along we were in the course with the lecture material and the assignments, etc., at the time that the test occurred. So, yes, cool. With respect to that, I think we can just move straight into our actual lecture material for today. Lots of celebration in the chat. Cool. Yes. What year is it this year? It's oh, I completely lost. Like, what a year of the... I want to say dog or something like that, but I'm probably completely wrong. You know, I've got a... I've only got a 1 in 12 chance, you know? So, last time we were talking about structured data types, and we were talking about lists. Lists being very, very highly similar to tuples, the primary exception being assignment to an element of a list is a valid operation, whereas assignment to an element of a tuple is an invalid operation. It's not possible. This is the essential difference between lists being tuples being immutable and lists being mutable. So this is going to get into some, you gotta understand a little bit about how the computer manages memory to really grasp the distinction between these two different types of things. So we'll go over it, hopefully in a reasonable level of detail. Year of the Ox. Oh, cool. That's cool. Yeah. Strong like a bull. Good. Let's hope the Ox doesn't bowl us over. Cool. So, mutability. Again, in order to understand this, you kind of have to understand how the memory management model works. So, we have this thing in computer science that we call the memory model in, like, capitalization and scare quotes. That it's like, this is a reasonable approximation of how the memory system inside of your computer works. So, everybody should know that memory holds ones and zeros. It holds on to the states of ones and zeros, right? You know, everything in the computer is ones and zeros. The memory, when it holds a variable, it stores it in terms of ones and zeros. You can think of it like this. Every memory chip is kind of composed of a bunch of intersecting circuits, right? These circuits have the ability to hold either a 1 or a 0 at each of the intersections, right? So when you store a value into memory, the states of these tiny little circuits are set in a particular manner. Of course, the problem that you then run into is, how do you get a particular variable out of memory without, and be sure that the information that you're gathering is the information that you meant to gather. So the way that memory is stored and retrieved is using memory addresses. So you can think of this circuit, right, as being a series of boxes. Each one of these boxes has a label, and each one of those labels has a long serial number on it. It doesn't really matter how the electronic circuits sort of manage these, but essentially, there are circuits which will find the correct the box with the correct serial number when it's given a serial number. These are, generally speaking, what is known as memory addresses, right? And this might seem like it's off on a tangent, but it's actually very important. So, when you have a segment of the memory that has a specific address, that memory, like when you are using a variable or a list or something like that inside of your program, basically at one point in the compilation process, at one point in the process that generates an executable a set of instructions from your programming source code, all of these variable names are swapped out for memory addresses. Like the computer decides what the memory addresses are going to be, and then it just everywhere that you have a variable name, it replaces it with a memory address, and the correct operations that hook all of that together. So, in essence, what am I getting at here? Well, when we're talking about mutability, we are essentially talking about data structures whose memory addresses can change, and data structures whose memory addresses cannot change. So, if you have a immutable data structure, something like a string or a tuple, once the segment of memory that has been allocated to that tuple exists in memory, it's never going to move, it's never going to change size unless it's been deallocated, unless it's been deleted. So, for example, if you declare a tuple within the context of a function, when that function returns a value, ceases to operate, all of the variables that are local to that function cease to be. They disappear. They're dusted by Thanos. So, the memory is freed, is another way of saying it. With a tuple, that memory segment will not, the nature of that memory segment will not change at any point during the use of that tuple, even when you're performing operations on it. So, just to illustrate this point, let's say we had a tuple, 1, 2, 3, right? And let's say we wanted to repeat it 3 times, right? You might be saying to yourself, oh, well, but that can't possibly be the case, Mr. Professor, sir, because this is a modification of that tuple right there. And I would say, the actual underlying memory that's associated with that tuple has remained unchanged. This is an operation that does not change the operands, right? So basically, once we start seeing mutating operations, we're talking about operations that will affect the operand, and non-mutating operations do not affect the operand. So, if you wanted to actually store this repeated tuple, you would have to do something like t is equal to 2 times 3. Then t is there, and you're like, oh, but Mr. Professor, sir, this certainly must disprove your claim that the size of tuples do not change. And I would say to you, what has happened in this case is a new segment of memory has been declared, it has been opened up, it has been brought into being that contains this new tuple. The new tuple has been put into this area, and the variable now points to the new one instead of the old one. So, when you're dealing with variable names that are data structures, like tuples, strings, or lists, or dictionaries or sets, as we're about to see, what you need to think about here is not, there needs to be a layer of abstraction in your brain between the name of the thing and what it's doing in memory. the name is different from the memory representation. So it's like you should think about T, in this case, as being a tentacle. It's like, technically speaking, we call these pointers. But pointers, pointer arithmetic, and all of that kind of stuff, that's kind of beyond the scope of this course. It's generally speaking, it's much more important to be able to manipulate them directly if you're learning a lower level language like C. If you're interested in the subject of pointers, I highly recommend going and watching the series of lectures that I did last semester on pointers that are up on my YouTube channel. That might be very elucidating for you. But this is how you should think about it. T is a tentacle that reaches out into a segment of memory, and it grabs that segment of memory, and that's what defines T as being sort of identified with that segment of memory that actually contains the information contained in the tuple. So the thing about this tentacle, though, is that it can be lifted off and put into a different segment of memory, right? So that is what the assignment, that's what the assignment operation does when it's operating upon a data structure rather than an individual variable. It's saying, okay, I was here, I am now being assigned over there, so just like that. That's what it does. So this thing is new memory. This is new memory. This T, the tentacle that used to touch 1, 2, 3 is lifted off of it and put onto the new one. So when you invoke the tentacle, it leads you to the new segment of memory. The old one, incidentally, is lost. Because we've lost our ability to find it, it no longer exists. I mean, technically speaking, the memory cells will still say 1, 2, 3, but because they have been, it's like, to say putting finding a needle in a haystack is like given the scales involved, it would be like finding a needle in a haystack that was the size of your house or the size of an apartment building. Because of the vast quantities of these tiny little circuits involved. So once you've broken the connection to a segment of memory, that memory that's broken now. So that's how tuples work. Tuples are static. Once a tuple has been placed into memory, it doesn't change. This is to contrast lists. Let me just see if anybody has a question about that bit before I go on to the next one. Nope. Okay. Let me just check, though, in case the chat isn't actually updating. Sometimes that's the case. Nope. Okay. Burp. There we go. Cool. So, with lists are mutable. So, whereas you can think of a tuple as a read-only segment of memory, with lists, you have both read and write privileges. So that's why you can modify the elements of a list. But there's more that you can do with a mutable data structure than just modify the elements. So Python does a heck of a lot of work in the background to ensure that lists have a number of dynamic operations that can occur on them. So, for one, we have appending. And let me just, let me declare a list, and I'll show you something. IDL, I think? Yeah, hex IDL. So, if you take ID, the ID function in Python, and then run it, print it. It's easier to read as a hexadecimal number. That's why I did that there. But this is actually showing you the memory address of the underlying data structure. So let me just demonstrate how this how this... Let me demonstrate the validity of the thing I was talking about with t. So this is the data... This is the memory address of t as it's written right here. So let's say we want to do t is equal to t times 2, right? What is the new memory address? See? It's different. The first couple of characters are different, but notice the F is, that's a hexadecimal character. So this is a different address, right? So in the case of lists, if you, you can modify a list without changing the underlying memory address, right? So if I did L at 1 is equal to 10, the memory address hasn't changed. And so let's talk about appending. Appending means adding something to the end of. So if I do L dot append some value, that adds that value to the end of the list. This is actually a very useful operation because in a lot of cases what you want to do is accumulate a list over the course of a loop's execution. Appending is an operation that adds something to the end of a list. So that's cool. So let's see if the memory address has been modified. Notice that the memory address has not been modified. So essentially, this list has grown by one element, but it hasn't moved in memory. Whereas, if you were to do the same operation on a tuple, t is equal to t plus 6, so you're concatenating. Oh, there we go. That's how you do a singleton tuple, is you include a comma there. It's sort of... Yeah, so the memory address has changed again. So this is new memory. So the concatenation operator is then a non-mutating operator. It will move the memory around in order to be able to accomplish this. It'll look for a segment of memory that's the size of the thing you want to create, put it in there, and then move the tentacle. Whereas, with the list, the tentacle has remained in the same place. It's the memory that has changed, right? So, that being said, there are limitations to this approach. The memory address will not change so long as there's blank space after the list that is in memory that can be allocated to that list. It's like, if memory is boxes, you've got your list, and then if there's an empty box at the end of the list, then the computer will just reallocate it'll resize the memory segment to include that empty box and then put whatever you wanted to put there in it. But yeah, so all of the operations in this table, you can think of them as in-place operations. That is to say, they're going to try not to move the list. They're going to try not to move the tentacle if that's possible. Now, if you try to append an element to a list and there's no room for it, then the computer has no choice but to move it somewhere else, which it will do. And it'll do all of this completely without you having to provide any input whatsoever as the user. However, that's, neither here nor there, I guess. So yeah, we've got append, which we've already talked about. We've got extend. So if you want, extend is like a mutating concatenation operator. It takes another list, and then it adds two lists together. It's like repeated appending for every element in the list that you want to extend the first list by. If you wish to insert an element, you can insert some index not at the end of the list, but at any point in the list using insert. If you wish to remove an element from the list and shrink it by one element, you can use remove. It removes it at the index I. If you wish to return the element and delete it, then you can use pop. And if you wish to reverse the list, you can use reverse. So it's kind of important to understand which operations mutate and which ones do not. So all of these are mutating operations. You might say something like, oh, well, I could write out reverse, or I could just do : -1, which is our shorthand. However, you'll notice that if we take a look, have we? Yeah, actually, it's still in the same spot. So, generally speaking, it can end up in the same spot, but still have been a mutating operation. Also, sometimes Python will look at particular cases, and like the : -1 is well known to be shorthand for reversing something. So it wouldn't surprise me if Python, when that was done to a list, invoked this guy. Python does a lot of that kind of stuff in the background. But anyway, does that make sense? What happens to the value at the index where E is inserted? Is it moved up or is it removed? It's just moved up. So if we have a list and L.insert at element 1, the value, yeah. There you go. It's an insert, right? It's like inserting a book into a bookshelf. You move all those books down and you insert the book where you want it inserted. So yeah. So now we get into an issue called aliasing. So that idea of the tentacles that I was talking about, this is going to be this is going to become important, because it turns out that you can have more than one tentacle that touches the same memory. So here's an interesting thing. We have this list L that points to this list. What happens if we assign L to S? If we ask for what S is, it gives us the same list. However, if we modify L at 1 and make it, I don't know, 19, there we go. We now have this new list where the element at index 1 is 19. But that's also happened with S. So this assignment operation has not duplicated the data structure, it has duplicated the tentacle. Right? So essentially, any modifications that occur to L will also occur to S, because S is pointing to the same thing that L is pointing to. They are two tentacles to the same box. And this can lead to trouble. So, yeah. So, if we say S is plus, if we concatenate to the end of S something else, like 7, you can see S now has 7 at the end. But L does not. Concatenation is not a mutating operator. It is a it's a non-mutating operator. So using a non-mutating operator will break this. It will create the new memory, and the new S will point to the new memory segment because it's been assigned to point to the new memory segment, and L will still be pointing to the old thing. So that breaks this. It breaks that up using the plus operator. Whereas using any of the using any of these rotating. Yee! Using any of these mutating operators will not break that. It will not break that behavior. So if S is equal to L, L is that, S is that, L dot append with 2 p's, the value 10. L's got 10 in it. S also has 10 in it. So another important distinction between mutating and non-mutating operations is that mutating operations will not break aliasing, and non-mutating operations will break aliasing. So that's what it's called, by the way. When two tentacles are pointing to the same segment of memory, you are said to have 2 aliases for that memory. Yeah. Are there any questions about that so far? I know this is a lot. You guys getting this? Are you guys, is this at all? I don't know. If you're good, give me a thumbs up. Yes. Could I explain what pop does? Yeah, I can do that. So, it's like remove, but you also get a return type. So if I say value is equal to L.pop at 2, notice that the value at index 2 has been removed from the list. And if I take a look inside of val, the value that was removed from the list is the return value of the pop operation. So it's like you pop it out and you keep it. Instead of, in contrast to the remove function, because it's very much like the remove function, remove is like hitting it with a giant mallet, and it just squishes it down to nothing and completely deletes it. Pop is like picking something out of the list rather than just smushing it. There you go. Cool. When will the submission deadline for A3 change on Avenue? As soon as I write that down and do that after class. Cool. A3 submission deadline on Avenue. Okay. Cool. All right. Moving right along. So, yeah, I've already kind of demonstrated this. If you modify an element, then it shows up in both of the aliases. That's because the aliases are, again, pointing to the memory. So here's an interesting thing, though. You can actually have lists that contain aliases to other lists. I'm not sure why you would ever need this, but it's possible. So let's say we had a list 1, 2, 2, 3, 4, right? Let's say we had a second list, S, that is 1, 2, L, 7. L is this, S is that. So despite the fact that it's displaying like this, it's still an alias. So if I modify L, L.append 8, then if you call S, that 8 will show up there. Incidentally, here's another important syntactic difference between mutating and non-mutating operators. With the mutating operators, you don't actually require an equality, or not equality, an assignment operation. It's not L is equal to L.append 8. It's just L.append 8. It's like calling a function on a line. This is actually technically called a method, We're going to see more of this once we start getting into classes in topic 8. But for now, you just kind of have to memorize or use reference to know which one of these guys you use dot syntax for. That's what this is called, is dot syntax. Which one of these you use dot syntax for, and which one of them you use like a regular function. But yeah. So this is a big, long thing. The question is, what is the end value of E? And then the answer is given on the next slide, I think. Or it's like if you take a look at this guy, it sort of illustrates it. So we've got A is 1, 2, 3. I'm just going to do this on the thing. A equals 1, 2, 3. B is equal to A. C is equal to 4, 5, B. A at 0 is equal to C at 1. D is equal to C at 2. E is equal to D at 0. So what is E? Well, A is 5, 2, 3. B is A, so 5, 2, 3. C is 4, 5, 5, 2, 3. D is 5, 2, 3, because that's just this element. And so E is 5, because that's the first element of D. So there you go. I don't want to belabor the point on this particular slide. So, slicing. Let's move along. Cool. So slicing and many other operators work uniformly on a sequence, on all sequence types. So, sequential data structures. As we get into sets and dictionaries, you will see that sequential data structures are not the only type of data structure, but all of the ones that we've covered so far are. So slicing. We've already talked about slicing to a certain extent. So let's say we had a string, right? Slicing 1, 2, 4 starts from element 1, ends at, or it's like close to without going over 4 as you can get, and then count by element 2. So, or count by 2 elements. So element 1 is A, element 4 is C, capital C. 1, 2, 4 is A, B, B. So it's exclusive of this guy, right? Again, this is the same rules for making a range object. And then if you count by 2, it'll exclude the one in the middle, because it'll just go this guy, skip 1, this guy, skip 1, that guy, skip 1, etc. Yeah. If you leave out one of these, it will assume to the end of the thing for the middle. It'll assume from the beginning of the thing if you exclude the first one. If you exclude both, then it will assume from the beginning to the end. And that's usually useful only if you've specified something here. Like if you leave all 3 blank, then you just get the string again, or you just get the data structure again with no modification. If you leave the third one blank, incidentally, it assumes counting by 1. So there you go. This can actually be a useful way to just break an alias without actually modifying the thing underlying it. Slicing always returns a new list. So there you go. If you want to break an alias, this is a good way to do it. Cool. This is a lot more fun when it's in class. I'm just gonna skip it. Basically, it's like a quick fire quiz round, which really the delay between you guys hearing me and me actually speaking makes this just impossible in an online situation, so I'm just going to skip it. But please feel free to go through it in your own time for, your own personal, edification. So, question: Why on earth would we use tuples versus using lists? So, there are two main answers. Number one, tuples are not subject to the aliasing problem that that lists are. So, if we have a tuple, this guy, and we assign another tuple from that tuple, I sure hope this works. The address of the tuple, the original tuple is so. The address of the new tuple is the same, which means it is the same alias, which means the slide is wrong. Don't worry about that. The real answer is that it's faster. So, because there's not all of this like back end all of these back end operations that have to go on, that are constantly moving a dynamic data structure around as it's being moved around in memory. The tuple is like the option that consumes more memory but is faster. You'll find in computing, you often have a trade-off between memory consumption and speed, oddly enough. Sometimes memory consumption and speed are correlated, and sometimes they're negatively correlated. So sometimes the more memory it takes, the more memory you have to operate over, the longer it takes to do so. Sometimes you can declare a little bit more intermediate memory and get huge payback in terms of reducing your runtime. Tuples are kind of like they play into that engineering trade-off. So now we'll move to sets. We have 10 minutes left. Let's see if we can do sets. So when we're talking about sets, we are talking about sets in the same sense that we are when we talk about them in terms of like abstract mathematics. So sets in Python are an attempt to recreate the functionality of sets from set theory. Set theory from math. So in math, when you have a set is like a formally defined thing. People often think of the jelly bean example. So, if you have a bag full of jelly beans, then that bag of jelly beans is a set of jelly beans. And, depending on how you define your set, that set can have different properties, right? But generally speaking, it's an unordered collection of objects. Now, in Python, we add to that the idea that there's no repetition. So a set in Python cannot have repeated elements. Sometimes in math, you get that. Sometimes in math, you don't get that. It depends on how you're defining things. But if you think of, for example, the set of natural numbers, that is a set without repetition. So, there you go. For example, the set of all even numbers less than 10 is 0, 2, 4, 6, 8. To say 4, 2, 6, 6, 8, 8, 0, 4, that's actually the same thing. So how do you define a set? A set is defined, we'll call it S, using curly braces. So 0, 2, 4, 6, 8. There you go. That's a set. So because we're doing sets now, the set operations that you're familiar with from your high school math classes will be applicable, generally speaking, in Python. So if you remember from sets back in high school, you've got two primary operations over them, union and intersection. So with the union operation, a new set is created that contains all of the elements in A and all of the elements in B. So it creates it's a new set that has everything that A and B has in it. The intersection is, of course, all of the things that are common to A and B. If you think about it in terms of the Venn diagrams, maybe I can look this up. Set operation Venn diagram. Yeah. Perfect. So we're not gonna worry about complement. So A intersect B is just the bit in the middle. A union B is everything that's in both of them. Difference is all of the elements in A that are not in B. And that's the same thing as here. This one. A new set containing all of the elements of A except for anything that is in B. And of course, if you want the cardinality, 3 guesses what we use to determine the number of elements in a thing. That's right, it's the length operator. Even though it, technically speaking, doesn't make any sense to think of sets as having a length, because length is like the length of a linear thing, and sets are unordered things that don't occur linearly. Nevertheless, length is still used. So, if you want an empty set, that's like that. If you want to put elements, if you want to declare a set with elements, you use curly braces. So let me make Q as 5, 6, 7, 8, 9, 10. Q. There we go. So S bar Q. Bar is intersection. Or sorry, it's union. The reason bar is used is because in other programming languages, bar means or. So 2 bars would be the equivalent of writing or for Boolean expressions in Python. So it kind of bleeds over a little bit, despite the fact that they would prefer not to think so. So all of the elements in both of the sets are present. 0, 2, 4, 5, 6, 7, 8, 9, 10. Now it's important to, just because these elements are in order does not mean that sets maintain order. Just keep that in your brain. You cannot assume an ordering over the elements of a set, even if the elements of the set have an implicit ordering, as numbers do. So, it's more like it's just sort of keeping them in the order that they are presented, for convenience, I guess. So if you wanted the union, that's S ampersand Q. And that is all of those elements which are common to both of these sets. So, you see? You see how the 8 is first this time? So, you can't rely on the things in a set being in any particular order. In this case, despite the fact that in both of these sets, 8 comes after 6, when we take the intersection, the 8 is before the 6, and the take-home point there is you cannot rely on any of the things in a set being in any particular order at any given time. Think of it as being random, and you'll be there. Difference. So if we have S minus Q, that's all of the elements in S that are not in Q, and if we have Q minus S, it's all of the elements in Q that are not in S. So, union and intersection are symmetrical operations. So it doesn't matter if you have T first or S first. It doesn't matter. You'll get the same result each time. Kind of like addition or multiplication. The difference operation, that the order of the operands does have an effect. So that would be the same sort of case as subtraction or division. So you also have our handy search operation. So 5 in S, false. 5 in Q, true. So there you go. You can use the same searching operations that you use on all of the rest of them over a set. Good. Okay, I've got some questions. Dictionaries are dictionaries not also defined using curling braces? How do we distinguish between the two? A dictionary, we're not quite to dictionaries yet, but you're absolutely correct. A dictionary is also defined with curly braces. A dictionary is a mapping between two things. So if I have apple being leading to pi and 17 leading to 9, that's a valid dictionary. Dictionary at apple is pi. Dictionary at 17 is 9. For those of you who like the very, very, very rough intro to a dictionary is basically a list where the indexes are not constrained to being numbers or in order. They can be strings, they can be booleans, they can be whatever you like, and they don't, like, we can use 17 without having defined 0 through 16, for instance. So the difference between a set and a dictionary is the colon. In a set, things are just sort of individual elements that are being thrown in there. With a dictionary, you are throwing in two elements separated by a colon, and that is the syntactic difference that leads to the semantic difference. Cool. Why use a set versus a list? Can you perform logical operations on lists as well? Normally, the only reason that you should use a set is if it makes sense to use set operations. It's in terms of like just abstract data storage, I wouldn't recommend a set. I would not recommend a set for general purpose data storage. I do recommend a set if, for example, you need to figure out, let me put it to you this way. If you need to take a list and reduce it to only those elements that are not repeated, so, or a string. So let's say hello world, right? If we interpret this string as a set, we get only those elements in the string that are not repeated. Sometimes that's going to be useful. It's a useful thing to do, so you should know what a set is. Or, you know, if the situation calls for an intersection operation, or a union operation, or something like that, that's when you would need a set. Oh my goodness, again? And that's a funny, it always freezes on, well, it doesn't always freeze on a funny face, but sometimes it does. I don't know why it does that. It seems to be on a timer or something. There we go. Cool. Let me fix my microphone too, because the microphone will have been junked up by that as well. Boop. Nope. I can usually tell if it's the condenser mic because the noise is so low on it. It's wonderful. Okay. Yes. So a sorting operation doesn't make any sense on a set because the elements in a set are not in any order. So reordering something that has no ordering doesn't make any sense. You can use sort on like a list, but not on a set. It's not an operation. Yeah, cool. Right. So, next time in class we'll continue talking about sets, and then we'll probably get into dictionaries, which we got into a little bit We got into dictionaries a little bit today, but dictionaries, generally speaking, are the useful one. Lists and dictionaries are the two most common data structures that you'll be using in this course and in your general life. What resources do you recommend if you are struggling after T1? Well, if you didn't do well on T1, first of all, it's really, really important to figure out why, right? It's like there should be enough data that you can collect from how you performed on T1 to know where your particular, where your knowledge needs to be supplemented. And once, it's kind of like your question is too general. I can recommend, general resources for studying, doing things in Python Tutor and doing the coding bat problems. I can recommend that, but I can't provide you, what you need unless you bring your test feedback to my office hours, and then maybe we can take a look at it and I can recommend something. I'm assuming then that you cannot do indexing or slicing with a set. That's correct. Set. There we go. What is set at 2? Type error. Set object does not support indexing. There you go. Can you convert a set into a list or a tuple so that it becomes ordered? Yes, I think so. Yep. There you go. You totally can do that. You could even do, passing something through the set notation. That's a way of eliminating everything that's, well, okay, that includes the braces and everything. But, it's a way of eliminating everything that is repeated easily and quickly. Haven't been able to fetch the feedback. Will the fet be fixed or... so right now we're working on getting the email server up and running so that your feedback will be emailed to you rather than you guys having to go... Because it seems like the fetch button seems to not work for mysterious reasons. And it's like, we don't know why. Some people can, some people can't. It doesn't seem to have any... people who submitted through Avenue seem to not be able to in general, and people who submitted through Jupyter can or can't with, I think it's, I don't know. I don't know why, but it's the case. So we're working on a scheme where people are going to get emailed their feedback. So hopefully that'll work a lot better. Yep. Okay. If you have any more questions for me, I'm going to be having my office hours in about 5 minutes on Microsoft Teams. So if you guys are if you guys are having any more questions, join me there. And to the rest of you, see you in a couple of weeks. Have a good break. Get some relaxation in. Don't get too overwhelmed with everything, I guess. I don't know. Take her easy.